What are some of the key things that we can really quickly just point out from yesterday's observation? There were like a couple things, right? Maybe 3 or 4 things that were somewhat important that we pointed out. What was one of them? Yeah.
For 60 and 30 degrees, it should be in the same area.
Okay, so complementary launch angles have the same range, right? Would that be how you would say that? So if we think about this, this is 60 degrees right here, and this is about 30 degrees, but both of those projectiles land at the target, which we'll call X on here. So complementary angles, good. What else? What else? I can think of 2 other things we talked about. That's one of the 3. There are 2 other main focal points that we had yesterday. Come on. This is not hard. We had like 3 things we discussed. You guys all observed. Think about what we physically did. Good.
There was the dropping things, where they push it and just dropping it and why they land at the same time.
Good. Exactly. So when things were dropped or fired horizontally, we said, like it was launched, remember, it was a 0-degree angle. That was the concept. So things from like a cliff like this that are launched horizontally or simply just dropped. Either way, they have the same time. Either way, they had the same time. Third thing. Again, the one going down is a drop. So if you want to write VI equals 0 here, that's fine. I'm going to use my pen's trying to. VI equals 0. Here it's just horizontally. Fire. Andre.
Yes, the steepness of the angle depends on how far the ball is going to go forward.
Good. So the angle is clearly the thing that affects the range of the projectile. So the angle theta affects the range of the projectile. What could we say? Let's make a generalization here, and I'm going to try and get some battery power back. I think I'm good. What can we really say? We could say the following. Let me move stuff up a little bit. As the angle theta increases, from where to where? Where do we have to kind of like cut off? We had a point that we talked about yesterday that changed things. There was a specific angle that we discussed. That was like an angle that was really a focal point of yesterday's lesson. What angle degree was that? It was a specific degree that we focused on. 45. So as theta increases to 45 degrees, the range, we'll call it X, right, increases. As theta went up to 45 degrees, the range went up. And we think about that, right? Here's a low angle, so a shot at a low trajectory, a higher angle. So you get up here, and then when we say start happening, what happens when you get above 45 degrees?
Well, if you get to let's say 90 for instance, you just do it straight up and down.
For 90, it's straight up and down. Good. So from 45 to 90, what's happening, Sophie? How would you categorize that?
It's like straighter and straighter.
In the vertical direction. Yeah. The launch becomes more and more vertical. So you get less and less range as a result, or less and less X, meaning the displacement. So again, what is X, guys? This is X right here. That's your horizontal displacement from here to here. And we call it the range in projectiles. Just with projectiles, it's termed the range. It's like, again, you use the word range for the Y in math, for the Y values. It's not the same thing. So just know this word range as a different use of that word. From 45 to 90, X, meaning the range again, decreases. What happens really from 45 to 90 is that you get a higher max height. You get a higher max height. Okay, so let's take a look at some examples. I didn't do this last year. Last year I went right into the notes, so I kind of wanted to see how this would work by giving you guys that demonstration yesterday. Because I'm thinking about it now the ideas at least are down pat. We put them into words just to like kind of symbolize what we talked about. But from what you saw yesterday, you should understand certain numbers now. So what we're going to do is we're going to soon break up velocity into components. Remember we've been talking about the X and the Y component with vectors a lot? We're going to do that with velocity. Because think about it. We've been talking about things that are traveling horizontally or vertically. Now we're going to look at an angle. So if it's launched at an angle, it's really going in what direction? Northeast, right? We kept talking about northeast. That's both the X and Y direction. So now we're going to take velocity and break it up into pieces. And we're going to look at our equations in pieces also. So let's jump right into this now. All right. So first, to define a projectile, we're looking at any moving object that can be modeled as a point. So why do we say a point? Why is it easier to model something as a point? What do you not have to worry about? You don't have to worry about it. But looking at an object as a point. Like, why would I model this person from the center? So this is the origin, right? There's the point. Why would I model them from the center?
Because like the variations in the shape would change it wouldn't be as exact, change the distance.
Exactly. So you want something that's pretty constant, whereas the center of this person's body isn't changing. If you call the foot where the person is, well, the foot is changing in height and stuff too. And the person's leg can come up like this when really the body itself isn't moving. You can move your foot without moving the overall body. So the overall body should be measured from a center point, which is usually called the center of mass or center of gravity. It's like a weighted average. It's the part of your body that would be considered the very center. Have you ever seen, there's a gentleman on YouTube that balances things, like ridiculous objects. He can balance anything on an edge. No one's ever seen this before? He finds like the center of gravity of where that would be, where the load would be sitting directly above. So for example, like a washing machine, he'll put it on one of the corners. He'll raise it up onto a corner, not an edge, a very corner, and balance a washing machine perfectly and move away. And it'll be sitting there, literally on like the edge. You know what I mean by the edge? Like the very corner part. What he's doing is he's finding this part right here, the center of gravity. He's putting that right above that location every time so that it's perfectly balanced. Because weight acts down from technically the center of gravity. So if weight's pushing down on that spot, it's perfectly balanced there. So projectile motion, we're just going to talk about two-dimensional motion. The second part we've already seen, free fall with an initial horizontal velocity component. So let me underline that. We've seen this. This was yesterday. It just means that it's fired horizontally. So this is this example where there's an object at a height and it's fired outward because it would follow a parabolic path. So that would be the path of the projectile here. So we know that this is projectile motion even though it's not fired at a traditional angle. And it's fired at 0 degrees, but because it's coming off of some elevation, it follows a parabolic path. If I fired at that angle on ground, is that going to go anywhere? Not really. So if I fire something horizontally on ground level, it will take that path still, but it won't go for very far, right? But it still is technically a projectile, because it does follow that path. When we fire things at angles, we're going to have to talk about the components of X and Y. And that's seen right here. Look at the figure here. So this girl is running forward, takes a jump, and as she's in midair, we notice that we have a velocity vector in the Y and in the X, meaning that simply in a long jump you would push not just out, but out and up. You would push out and you would push up. So this is the velocity up and this is the velocity out, or to the right. Okay, that's the idea of a projectile being fired at an angle. There are two types of paths here. What do you think the difference might be? What would the difference account for? And I'll give you this much. It's not referring to angle. Why would there be two different paths? One could be
Maybe like the force from like the one that's gone higher
has more
harsh back.
initial velocity.
Yeah.
Okay.
Initial velocity.
So if you hit it harder, like take a volleyball. If you serve a volleyball harder, it's going to go faster, right? Does that make sense, like logically? So you think about the initial force that's applied, and the one that is applied with a greater force will probably go further. Good, that's one thing. There's like 5 different answers to this. It's not just one answer. Sorry, so let me give that premise.
The rotation of the ball, like where it hits your own head.
Okay, so if the
If
ball,
it like hits you here, it'll go straight up. If it hits you here, you're heading
so the
up.
position that the ball
Yeah.
hits you in the head. Okay, the position of the ball hits you in the head. Absolutely, that works. Chris?
The speed before the ball hit the person in the head.
Okay, so if the ball is coming from somewhere else with a high velocity, it has a lot of energy, so that energy has to be rebounded. If you've ever seen, like in a baseball game, you'll see a pitcher, someone like, back when I was younger, like Randy Johnson threw like 102. Now it's, Chapman on the Yankees throws like 101 or something every pitch. The harder the ball goes in, the faster it goes out, or the faster in, faster out, meaning it has more energy, so the rebound velocity. Good. What else? I'm thinking of one other one too. There's just one more I can think of, and it's one I do want to discuss.
The girl like jumping to meet the ball gives it more force.
That's absolutely true also. Not the one I was thinking of though, but you're right. The girl jumping up is similar to what Isabel was saying with how much force she applies, that initial velocity. her jumping up gives it more initial velocity. So it's not obvious. I should kind of answer this one. So one is the theoretical, one is the realistic one. So theoretically, it should go along that blue path. But realistically in life, it'll take a path that's shorter and that's not symmetric. Why is that? What do we keep talking about that we always neglect? Yeah, so with air resistance, parabolic paths are not actually symmetric. So let's jot that part down here. Okay, so the actual path of a parabola is not symmetric. A projectile rather. The actual path of a projectile is not a symmetric parabola. So it's with air resistance on the inner part here. Okay, that's with air resistance. All right. We've discussed that enough. There's no need to beat it. So this was what we did yesterday, and just a quick visual of this. So if you guys recall from this apparatus over here, we had one object that was dropped, one that was fired horizontally, and twice it was really close. The first time it was good. The second time it was like perfect. The sounds are almost identical when it hit the ground. And this is exactly it. This is exactly the experiment we did with what's called like not a time lapse. Oh my gosh, I have the phrase here for it. What is the actual term? A strobe photograph or something like that. It's an older machine that was used that took a lot of pictures by holding the lens open, and a flash would be going every 60th of a second. Mr. Hall and I were discussing this yesterday actually, because I was like, I want a good way of explaining this and showing this. And I told him I had that. He said, "Oh, that's pretty cool because it simulates that, the horizontal and the drop." But if you have an actual, whatever that's called, the photo strobe thing, you can actually have it flickering and take pictures, and it gets a picture every time. So it's a really cool thing. Anyhow, the concept is that the one in yellow is fired outward, yet it still falls at the same rate. Why might we use this, and where might you see this? Because we're about to do something that involves this concept. But can anybody predict maybe where we might see this? Why we might utilize this information?
And problems like where it tells you like a person might hit like two of the same object, but like it would like land at the same time.
Okay. Yeah. So when you're looking at two objects that are one dropped, one fired, and trying to determine differences in like range and time.
If someone's like gonna jump off of something, maybe that would seem like, because like depending on the way that they would jump off,
Yeah, if you like jump off of a cliff or something gets kicked off of a ledge or thrown out the window of a building, like anything like that where it just initially has some velocity in the x direction. A baseball pitch would actually be this, believe it or not. Anything that's like literally thrown horizontally will fall at some little rate. So you're going to see that curvature some more than others. When we look at projectile motion in a moment, though, what we're going to recognize is that we can look at components. I keep saying velocity in the x and y. So when we talk about a problem where it's fired this way, I want you guys to be thinking about this in the y direction. Does that make sense? So in a moment, we're going to see problems where they're fired horizontally. I want you to think about the free fall motion for the y direction. For the x direction, we'll discuss what we're going to talk about there. But for the y, keep free fall in mind. Okay, keep free fall in mind. So let's take a look at this example. So in a bridge is 300 meters above a river. We use Tom Cruise as our actor. Tom Cruise, I started using Tom Cruise a while ago and then continue to use him. I don't know why. Tom Cruise jumps off a bridge to avoid a sticky situation he's gotten himself into. He jumps off of the bridge by running off the edge in the horizontal direction. If he hits the surface of the water after a horizontal displacement of 50 meters, what's the velocity with which he jumped? So there's a lot of information here. What do you think the first thing is that you might want to do for a problem that this involves?
Mark that when x is 50, he's going to be on the ground.
Okay, so maybe a diagram to show that? Would that be agreeable? Yeah.
You put the bridge.
I think you should always draw a diagram with these problems. It will really help you a lot to visualize. A short diagram in the upper left part. Yeah.
List your givens.
Second?
List your givens.
And in the diagram or on the side, either one. We're going to talk about how it might be useful to list your givens in the diagram sometimes now with variable names. So let's do givens and diagram kind of together here. So we have a bridge that's 300 meters above a river, right? That's the first thing we have to consider. So that's going to be in our diagram. We know that there's a horizontal displacement of 50 meters. That's going to be in the diagram. And we're told that he jumps off by running in the horizontal direction. And then it says, what is the velocity? So that's the last part we need. Oh, with which he jumped. That's important there. All right, so with a diagram, I might consider these things as variables. I'll draw a simple diagram first. So a simple diagram, oops. Give it the color to be black. So I emphasize the horizontal velocity by drawing a horizontal vector. It's really important that you would do that in the diagram, just to recognize to yourself that this is a problem where it's fired horizontally. For this problem, it simplifies a lot when it's fired horizontally. When it's fired at an angle, it'll be a little more complicated, and we'll get into that more. Okay, but when it's fired horizontally, it means that the velocity is all in the x direction. Write yourself that note right now. That's called Vx right there. And that's what we're really looking for. There is no y component. It's not at an angle. If this object were launched at a 30-degree angle, it'd be going up and out. This is just going out. It's not going up at all. It's only going down because of gravity. You see what I'm saying? This object is not moving in the vertical direction due to any sort of push from the launch pad, only due to a push or pull, really, from gravity toward the Earth. So that's why it's getting pulled down, but it's not going up. So this is all x. We have to really keep that in our mind. So what would I say that the velocity is in the y direction then? If this is all in the x, I'm telling you, what do I list the velocity in the y as? 0. Okay? Now, here's the interesting part. The velocity in the y will change because of gravity. Which way does gravity pull? Down, which changes the y velocity. So what I need to do is technically say that vi in the y direction is 0. This is starting to list some of my givens on the side, because I don't want to draw it because it's 0, so I shouldn't give it a vector length. So I don't want to draw an arrow right now. If it were at an angle, I would draw both arrows on there. Why am I calling Vx just Vx? Why am I not changing it to Vix? Why am I not calling that one Vix? And I'm doing it for a reason, so what's the reason you think, Chris?
It's already running in the speaker for a job.
Okay, but why did I call why did I call this VIY, not just VY? Why did I emphasize initial?
Because it starts to curve down at a certain point. It doesn't it starts at a certain point that we know about.
Okay, more than that, Chris. We said it starts at 0 velocity, but because of gravity, what's it going to do?
It's I was thinking of some different answer. Yeah.
James?
Change.
It's going to change in what way, James?
So you'd have like a second, a final one.
Yeah, meaning like it's going to accelerate downward. When you drop an object, it gets faster downward, right? It gets faster and faster. So the y velocity, you don't listen carefully, is going to change. So I have to designate this as the initial, meaning the velocity in the very beginning is 0. At the end, it's going to have velocity in the y direction. Because this object is now moving which way? It's moving to the right still, but it's also moving now down. When it's moving down, it's got to have a y velocity. So the y velocity will change. So I'm designating VIY, but I'm not designating VIX. How come? Why am I not designating VIX? And I'm not doing it for a reason, for a specific reason.
Because it's staying like straight in the horizontal direction. So.
Can somebody clarify what he's saying? That I know what you're saying, but that doesn't make sense mathematically what you're saying. But I know what you're saying. You're saying it's staying straight. You need better vocabulary. Not what it's actually doing. Yeah, the velocity is constant. It's always this direction for the x. Think about it. What changes velocity? What's the one thing that can change velocity?
Gravity.
Okay, in this case, it changes it. Agreed, very true. But in general, gravity is a type of what? What's the word? Gravity is something, because it's measured in meters per second squared, which is measured as what?
Acceleration.
Acceleration. So is there any acceleration in the x? Which way does gravity act again? In the y, doesn't it? So the only acceleration that this object is feeling is being pulled down. So the velocity will change here. This is a really important part. But it will never change in the x direction because we are neglecting what again? What do we keep saying we neglect? Air resistance. That's what would be a decelerating force. Imagine I'm flying through the air. Wouldn't air resistance slow me down? Isn't it called resistance for a reason? That would be a negative acceleration, which would be decreasing my velocity. That's why in that real picture, it doesn't make it very far, because air resistance slows you down. So the negative acceleration here that we're neglecting is the reason we can call this just Vx. Now, you know what I sometimes call it? Sometimes I actually call it V bar x, because the bar above means constant. This can mean constant or average depending on the connotation or the context, I should say, the context. So sometimes I even put a bar here to represent average. It's not going to change, okay? It's not going to change. So the other things we need to label, I know that was a long thing, but we really need to know this. It's one of the key things that we're going to emphasize over and over again, that the x velocity never changes. We need to label the height, right? The bridge height is 300 meters above the river. So what do I label y as? If he starts at the top and ends at the bottom. I'm giving hints, right? I'm prompting you with this. Starts at the top and ends at the bottom. What is y equal to as a result? What is y equal to? What do you think? What do you think? What do you think? Isabel, what do you think?
Is it negative? Is it negative 300?
Very good. Negative 300. Okay, because again, it starts at the top and it ends at the bottom. So I'm going to call y negative 300. If it was an object that was launched from the ground up to the cliff, y would then be obviously positive. Whatever that number is, 300 in this case. And then x is to the right, so that's positive. I don't have to worry about that. And we're told it's a horizontal displacement of 50 meters. So the diagram helps me a little bit just to visualize what's going on. And the question is, what's the velocity with which he jumped? So what's the initial velocity, or what's the x velocity? Because that's the way he jumped. Tom Cruise did not jump out. Let's make believe for now. Okay, I know he could have been, or he did really. But imagine he just was running from somebody, didn't see the edge of it, and just ran off, hypothetically, okay? It's not really realistic, but horizontally fired. So this is the y direction. Let's also designate the x direction. And it doesn't matter if I put the y on the left or the x on the right. I'm going to switch back and forth. In the x direction, I know we're looking for Vx. I know we have a displacement. In the y direction, we have a displacement, so we can label those accordingly. So in the y direction, we have a displacement of negative 300 meters. We have a displacement over here of 50 meters. We don't have the velocity in the x. That's what we're looking for. We can put a question mark there. What's the acceleration in the y direction equal to? What's the acceleration in the y direction only? Gravity. Now, if I really want to be specific, and I've done this before, sometimes I put a subscript. I call it AY, just to say that it's the acceleration in the y direction. I don't have to very often because, honestly, there is never acceleration in the x direction. What did I just say? That the velocity is what? What was the word that Anne helped us with? It is constant, right? So there is no acceleration in the x ever. Ever. So you can start by writing now if you want a equals 0, but you can kind of drop this at this point. You don't really ever have to even write it because it's never going to exist in the x. What's the only formula since we started this year that doesn't involve acceleration? There's only one. What's the only formula that we've used that does not involve acceleration? Because we don't have acceleration, right, in the x direction? Rick, what is it? So give me a formula.
Distance over time.
Speed is distance over time. There was another version of that, though, for velocity. It was velocity equals, instead of distance, displacement over time. Very good. So this was our formula that we've started the year with. And that's the formula we can use in the x direction. Why? How come we can use that formula? It doesn't involve what? It's the term that we don't have in the x direction. That's the thing. Velocity is a constant, so we don't have, as a result, acceleration. This is the only formula, look at it, that doesn't have A in it. Look at all the other formulas in the beginning of the year. All those other formulas have A involved in them, in that first chunk on the front of the sheet. Okay, all the ones you've learned, at least so far. So you know what I'm going to do? I'm going to be a little bit more specific, and I'm going to call this V. I'm going to call it V bar X again, because I'm in the X direction. It's the same formula. I'm not changing it. Again, I want you to recognize that this is the exact same formula. I'm just changing it to V bar X. And I think on your formula sheet, I wrote V bar for average speed there, or average velocity. All right, so what's the problem now? We want to figure out what is the speed or velocity with which he jumped. So what are we looking for? Vx. What's the problem though? We have x. What do we not have? Yeah, we don't have time. And there's nothing we can do in the x direction. This is the only formula we've got. And look, we've got two unknowns. Does everybody see this? Remember you studied systems of equations in the summer packet? Substitution method, remember this? This is why you did this. We have two variables unknown and only one equation. So what do we need another of? To solve a system, if I have two variables, I need two equations. And I only have how many? One. So I need another equation, right? And if I'm done in the x direction, where do you think I should look? What do you think? In the y. Is this logical, the format I'm going through? I'm doing this slowly on purpose, because if you get this in the beginning, it makes this unit pretty easy. So you have to list your equation that you're going to use. You're missing two variables. Can't do much. So let's move on over and find another equation over here that we can somehow link together. Okay? Looking in this direction now. I need to get time because I need time here. Does everybody see that? I need time here. So let's put t equals question mark in the y direction now. Because if I want to get time, that's my unknown variable. And I want to list that so I can physically see it in front of my eyes. I'm looking for this, so I write it over here as a result. What equation can I use that involves these variables right here? We have one equation. Now we have to use our equations with acceleration. Got it, Isabel, again?
Yeah, it would be y equals VIT plus 1/2 AT squared.
Well done. Okay, the only one that works for all of these four variables is that exact equation, y equals, now, VIT, I'm going to call it VIYT, again, just changing my subscripts according to the y direction only, plus 1/2 AT squared. And what are we trying to figure out in this problem? What are we solving for? What are we looking for here? Yeah, we're looking for time. And at first it seems like it's going to be difficult because look, oh, it's linear and it's quadratic, it's both. But what do you notice that happens? It's pretty nice.
The VIY is 0.
Very good. This is 0, isn't it? Look, we said earlier, remember I kept talking about this, I said, remember, it's only fired horizontally, so the vertical velocity to start is 0. So this whole term drops off. That makes it very nice. It's very convenient. This whole thing goes to 0, because 0 times t is 0. Even if t is some number, 5, 7, 8, it doesn't matter. The zero product property tells me that this whole entire term is 0. So that makes the equation just y equals 1/2 AT squared. A very useful equation that you're going to see a lot. This is very useful for free falls, right? When you drop an object, this is pretty much what you're doing. No initial velocity. This is the free fall equation, really. As a result, we can solve for t. We know y, it's given. We know acceleration is given. Let's find time. Everybody see you can find time numerically? You can solve algebraically by moving the 1/2, moving the a, and getting rid of the square. Or you can plug in your numbers at this point for y and a. If you feel more comfortable plugging in numbers, do that. I'm going to solve with the algebraic approach first. But if you want to plug in numbers, I'll show that as well. So algebraically, multiply by 2 on both sides. Divide by a on both sides. And then take the square root. This would be the algebraic approach. But if you want to use numbers, I'll put a little detour here in red. Plug in at this point. Y would be negative 300. And it would be 1/2 times negative 9.81 t squared. And then carry that down and solve for t. So take either approach. Plug in numbers, that's in red. Or in black, take the algebraic approach and at the end plug in numbers. But either way, the goal is to solve for t as a numerical value. I'm going to give everybody a minute just to practice it, and then I'll take the answer, just because I know a couple of you have it already. So again, take the red approach. I'll zoom in a little bit so you can see this better. Take the approach in red if you'd like to plug in numbers. If you'd like to solve algebraically, take the approach in black. It's totally up to you at this point in here which way you want to approach it, but I will give you one hint. There can come a point in time where you have to solve algebraically, so you should practice this. And I'll tell you there will, because sometimes we won't know all these numbers here. And then we have to solve algebraically and plug it into the other equation over here in terms of other variables. So plug in the numbers, but still jot down the stuff I just wrote for solving algebraically. Right, multiply by 2 on both sides to get rid of the 1/2, divide by a, and then square root. And I should put what symbol in front of the t, or in front of the answer for time? What symbol should I put? Because I took a square root. Yeah. Okay, technically it's plus or minus. Whoops. I know it's not going to be minus. I don't have to really put it, but I'll put it here to be nice right now. Okay, but really it's not going to be a negative time. You're never going to use a negative answer. The negative time would be going back through the cliff in that direction.
So for like in this instance, on like a problem, let's say on like a test or something, would you care if we just wrote it as a positive? Or
No, I would, because in this context, it's acceptable not to write the plus or minus. Okay, but if that's not the case, like there will come a time where you have to solve a quadratic that's not solving for time. It might be solving for x, and x can be displacement. That can be positive or negative. So you have to recognize that only right now, because of time, is the reason we're not worrying about it. But when you do the quadratic formula, Joe, you can't ignore the negative roots. So you still got to do plus or minus square root of b squared minus 4ac all over 2a. Because even though it could be plus or minus, the answers could both still be positive times. We saw an example of that. We're going to see it in like 3 examples. So still recognize that when you have the quadratic formula, you should recognize the plus or minus there. But solving algebraically, being able to do this, is different. Because you know it's going to be positive or negative, right? The answer. You know for a fact. But with the quadratic formula, they could both be positive roots. What do I get as a number here, Will? I saw your hand jump up first.
Around 7.2.
Around 7.2, is that agreed? Do others agree with that? 7.2? I see no, I see yes.
7.8.
7.8? 8, check. Oh yes, okay, so it was 8. Okay, good. So 7.8, and that's an approximation, so I'll put the approximation symbol. Now if I know that's my time, I can slide right over to the x direction and go ahead and solve for Vx. Let's just go ahead and plug in for Vx over here now. And this problem becomes really easy if we take this kind of an approach. That was in meters, this is in seconds. Look at that, how convenient. What are the units of velocity? Aren't they meters over seconds, meters per second? And we have meters over seconds. 50 divided by 7.8. Should be around 6.4. Is that what you're getting? Around 6.4? 6.4 meters per second. It's actually pretty fast. Taking a 5-meter jump every second is actually really fast, you know? I mean, 1 meter is like a step. This is 1 meter per second. Think about going 6 times faster than that. That's actually quite fast. Probably a little too fast, actually. Somebody Google real quick fastest human speed and convert it to meters per second. I'm curious what it is. I feel like it's only around like 4. I always like to challenge myself on number sense when I don't know the answer, you know? Like, what do you think, honestly? If this is 1 meter per second, how fast do you think the fastest human speed is? Can somebody actually go 4 meters in a second? Can they go that fast? 5 meters per second even? What does it have? Conti, I see you're looking it up. 44 what? Oh, so type that in Google. What is it?
So it'd be 27.8 miles per hour.
Dang, 27 miles an hour a human can run? That's got to be like top speed sprints. Same goal. And to meters per second, type in that number and put 2, the word 2, and then n/s. It's a good way to convert, guys. Check your conversions on this. What do we get, Ken? It's long distance. Long distance, the average speeds are like probably like 15 miles an hour. Because a sprint is obviously like insane. Those guys are using all their energy. I'm sure. What do we got? It's not working?
12.517 meters per second.
12 meters per second? All right, so never mind. Then this is reasonable then.
That's 28 miles per hour.
And that's from 28 miles per hour? So, okay. So this is pretty much half of that. This is like 14 miles per hour. The concept makes sense, right? You want to think about the appropriate equation. Now here, jot yourself a note. This is where you have to start writing down conclusions. In the x direction, this is pretty much always going to be what you have. Pretty much always. You're always going to use this equation because you're always going to have 0 acceleration. So write yourself a note that you're always going to use this equation in the x direction every single time because acceleration is always 0. Your x velocity can change, and if it's at an angle, it'll only be a component, but you're still only going to use that equation right there. And let me show you one last thing, okay? Let me show you one last thing. The other thing we could have done is taken this expression right here for t, for time. Just take a quick look up in green. And I could have taken that value and just plugged it in for time right there. And this equation would have become the following. And that's fine, because that's using real direct substitution method. Remember, with substitution, you actually plug in the variable expression into the other one. So even though we plugged in and found a number, which worked, and it worked fine, if I wanted an expression as an answer, for any of you that might want to take AP Physics next year, you will do this, guaranteed. You give an answer, there are no numbers in the problem. None. Imagine this problem with no numbers. This is your answer. You're done. This is the velocity in the x direction that we were looking for. If you plug in 50, and then you plug in for this comes out to 7.8. That's that number right there. So this is the actual answer, expression-wise, or variable-wise, or parameter-wise, whatever you want to say. Okay? And in reality, you could even write that better. Because the square root of an a in the bottom, take a look at what this will become. Okay, that's what it really would be. Because remember, when you divide by something and you have a denominator in the denominator, it bumps up to the numerator. So root a is in the bottom here, that goes up to the top. So that's actually the real answer. This is not something you have to do on my test. Even this part you don't have to, but it would be good to do it. If you got to this point, honestly, and then made a mistake plugging in, I would probably only take off like a quarter or half a point at most. Because all the work is right up until here. So you don't even have to use numbers or worry about numbers for a while if you like solving algebraically. But it's got to be right, obviously, and then you plug in numbers at the end to get that like last half point. Okay, because this is really the actual solution right here. This is what? This is an approximation of the value, right? For that instant in time, for that set of parameters, 50, and then what was it? Negative 300 and negative 9.81. Hey, all I want to do, you have like a minute or two, just list down the givens here. Try and draw yourself a diagram. We're going to have you about 2 minutes. Try to list the givens and draw a diagram, and we'll pick up with this one next class.
So 150 meters a second should be the Vx. Yeah, because
That seems appropriate, right? Because which way do planes fly, we assume? Let's make that assumption. Sometimes you have to make assumptions in physics. Which way do planes fly? Horizontally, you would say, right? This is, let's say it's at cruising altitude. That's an assumption that has to be made because there's nothing about an angle given. So it's not flying at any angle, we can't say. Doesn't matter which column I make x and y. I usually go x then y. The last problem I did it backwards, so. So these are some of the main things you should have down at this point. Okay, these are some of the main ideas. We're looking for x, which means we also need time because it's in that equation. So again, we're going to use time. What I think I'll do is, tomorrow, I have you guys tomorrow, right? Is it a double tomorrow with you guys? Right? So we're gonna do a lab, and then I think what I'll do is I'll allow you guys to start this problem together and just finish solving it. Okay, but we'll go into it more tomorrow. Feel free to take a look at the idea. I promise this is not hard if you practice this and use the methods that I'm showing you. So I went deliberately slow today, which I've never done before, and I prefaced it with that other lesson. So I'm really hoping that helps. Okay? Because this can be a difficult topic for students in the past. They choose not to really push themselves, but this is a topic that you can do well. Here. This is all the things that we wrote down to start. And we saw that this plane was traveling horizontally. So when the package is dropped, it's really just moving horizontally to start, and then it's going to start to fall. So we can consider this a horizontally fired projectile. That's the category that we're constantly using here. Horizontally fired projectile. Because again, if I'm moving, and you could do this with your hand, and if it's not obvious, please feel free to do this. Take an object and just walk with it, right? As soon as I let go, the path that it travels on, as soon as I let go, follows that parabolic, or I guess I'd say half parabolic path. So again, as soon as you let go, it's going to take that curved path. That's what we're seeing right here. That's the curved path we get when something is fired horizontally. So although the aircraft is not literally firing this package, is not shooting it horizontally, it's just dropping it. But because it was moving horizontally at first, both the care package and the plane are moving horizontally. And then as soon as it lets go of the care package starts to also move vertically, which makes it a projectile. Okay, it makes it a projectile. But again, which way was it moving initially? It was only moving horizontally, which allows us to say the following. We can say that the velocity in the y direction to start is now 0 again. Again, simply because of the fact that this does not affect the problem here. This is not considered because it's like a free fall. It's like you're dropping it. Okay, because you literally are dropping this object. The only way that it's moving before you drop it is horizontally, which is why it has some velocity horizontally to start. So let's go through this process again of how we're going to take an approach. What's the only equation that we're going to use in that x direction? What's the only equation we talked about? Good. Vx equals x over t, or just v equals x over t. Okay, and I've been using that symbol above the v to mean constant. If you want to, you can. If not, it doesn't matter. But that's the only equation that we're going to use in the x direction. But again, what do we recognize? What's the problem here? What's the problem that we have? Good, a lot of hands. What's the problem?
Missing the time?
Yeah, we're missing the time. We don't have the time here. We're looking for the displacement. And I purposely made sure that these first two problems we're doing, they're kind of easing you into it. The idea that, you know what, let's make it obvious what we're missing. And we're missing time. So if we solve for time here, or if we try to figure out what time is, we can plug it in here. Where do we have to go to figure out time in this case? James? The y direction. And I didn't use this phrase last class, but the value time is actually called a linking variable, meaning that it links two separate equations together. So time is the only variable that kind of overlaps between the two. Acceleration in the y direction is negative 9.81, while acceleration over here is 0. So this is not a linking variable. These velocities are different, meaning they're not the same. It's not a linking variable. Displacements are different, but time, whether I'm moving in the x or the y, time is completely independent of those, right? Time is time. It's not like it matters if I'm looking in the x or y direction and I look at it. The time it takes for this to hit the ground, whether I determine it in the x or the y, should be the same answer either way. So that's our linking variable. It links the two pieces together. So yes, let's find time in the y direction. So that's what we start by writing. And again, this is a rather simple problem, right? Why is this an easier problem than it could be? What's the one thing that makes this an easier mathematical problem for us? More than that, James. Not just you have to plug in, but there's something else that makes it simpler before we get to that stage. The initial velocity is 0. That helps us a lot, which enables us to just plug in and not have to use the quadratic formula. So let's go ahead and look at our equation again. Here's our equation. When we look at this equation, this first piece drops off again. We don't need VI because VI is 0 in the y direction. So this piece drops off, which allows us to solve for t. If it didn't, we'd have to use a quadratic to solve for t. Okay, we'd have to use a quadratic to solve for t. But it does, so we'll make it nice. We can use the same generic solution as last time if we want to, because it becomes the same equation as last time. Was that yesterday or the day before? It was yesterday, right? Yesterday? In yesterday's class, we solved for t here. And I said you could plug in numbers or you can solve with variables. Either way works. And that's still the case. Either way works. But I must say that we've already solved this in terms of variables once. We did it yesterday. And we had an expression for t. T turned out to be 2y over a underneath the square root. That was yesterday's answer when we solved this. So I'm going to write it down right away, because I remember it from yesterday. Okay, this is the exact expression that was used yesterday. It's the same, God bless you. It's the exact same setup and arrangement. This is identical right here as to what we had yesterday. And then we just solve for t. Multiply by 2, divide by a, get rid of the square by taking the square root. Again, it's plus or minus, but I don't care about negative times. So for this specific problem, because I can say, you know what, it would give me a negative answer for time, I could ignore the negative root here. Remember though, if you use the quadratic formula, and you didn't have vi 0 right here, and you have to use the quadratic formula, you can't ignore the negative root. It's still got to be x equals negative b plus or minus the square root of b squared minus 4ac over 2a. You can't actually ignore that plus or minus when it's in the formula, but here you can, because time has to be either positive or negative, and we can't have negative time. So when we plug in, we'll get a value for time. And if you remember, I showed you at the end of class, I'll pause this for a sec. So here's what I'm going to plug in. I'm going to go ahead and plug in root 2y over a. I'm going to plug in 2y over a in for t. I'm sorry, in for t. I wrote down t at the end there. I meant to write down x over here. So if we figure out what these values are, it looks like the vertical displacement is negative 500. That's for y right here. The acceleration is negative 9.81. The velocity in the x direction to start was the velocity of the plane before it dropped the package, which was 186. That goes in over here. And we could just multiply this through to get x. But please, when you're doing this, make sure you take the square root of whatever this is first, right? So perform the operation under the square root. Do your 2y over a. Take the square root of that, then multiply that answer by vx. See what you get for x in this problem. And I'm trying to do this on purpose in a way that you don't actually ever get time. Okay? You don't actually solve for time here. You don't need to get time. The problem doesn't ask about time. Sure, you could find it and then plug it in here for t, but I just plugged in the whole expression. So I don't ever have to get time. I can just go ahead and plug into these variables right here because they're all known. So again, the point, here's what I did. I plugged in this expression right here
You said section 2 and 3.
in for time. Around 1877 is looking like the number we're getting here. Around 1,877 meters. So for this to work, think about that. Who runs track? What's a mile in meters? Anybody know what a mile is in meters approximately?
3,600.
No, not 36. You think of a different
16.
number?
It's
16, yeah.
yeah.
Around 1,600. So around 1,600 meters is a mile, and this is 1,877 meters. So this projectile has to be dropped a mile before they even reach the target. And this is not considering air resistance whatsoever. So we have to consider all those things. What do you think would happen considering air resistance? Would it have to drop it closer or further from the target?
It depends which way the air is pushing.
Good answer. I like that, Rodrigo. It depends on which way air is pushing. If there's a wind that's actually helping, like what we call that a tailwind, right? It's coming from behind. A wind that's helping the package, then you can drop it way earlier and it'll still make it. But if the package is going this way and the wind is pushing back this way, you need to drop it closer because it's not going to go as far because the air will slow it down. Traditionally, we consider air resistance as an opposing force. But in reality, it can help the package also depending on which way the wind is blowing. But that's hard to also consider because wind changes direction as well, right? That's why nowadays, instead of a package being dropped and being like, okay, let's hope it makes it there, if they're using some sort of a missile, it's guided. It's always guided. It's got what are called feedback systems in it that say, oh, you know what? That gust of wind pushed me to the left 2 feet. Let me adjust this flap to reorient myself, to go back on track. And it has a target in mind, so it's able to self-correct at a rate that is like instantaneous. It self-corrects at like milliseconds. So as soon as there's a little bit of a pitch change because of the wind, it alters the angle of one of the flaps and readjusts. That's how an airplane works too. An airplane is literally doing that every single moment. Every time an airplane gets unstable, the flap adjusts instantaneously to level back out. Ever notice an airplane, you feel like little rockiness, then sometimes you do feel turbulence? Thank God for feedback mechanisms, or else turbulence would be way beyond. Like planes would be coming down. They wouldn't be able to make it through. So the plane itself senses the turbulence, and it actually feels the gust of wind as soon as the dynamometer or the angle measurement, it's not a dynamometer, actually it would be, I don't know if they would use to measure angle measurement. It would be some sort of a ball, fluid that moves and measures that it's moving left to right. But it measures pitch. As soon as the pitch changes, it's going to react automatically to fix the plane. And that's what would really happen with something like this. It wouldn't actually just be dropped.
Should be
Good?
good. Yeah.
All right, so I want to print it. Let's go to the next slide real quick. Take a quick look at the next slide before I get started. Look at it yourself and just make sense of it. This has to do with our vectors again. Try and draw yourself the triangle that we've been using the whole time. 1 second. If we did get time, by the way, in this problem, it would have been around 10 seconds. This problem here, this topic, and then the whole next chapter on forces, because think about a force. If I pull on something, I'm never really pulling horizontally. I might be pulling at an angle. I'm not necessarily lifting up and pulling at 90 degrees. It's always really at an angle. So we need to break things into those components. So this idea of velocity being broken into components goes along with that idea. So we've talked about now tossing an object up and moving left to right. That's vertical or horizontal velocity. But now we're going to start to focus on things where the velocity is at an angle. Okay, and if it's at an angle, well, we know, and let's draw that. So let's draw a velocity vector at some angle. Let's say the velocity of this projectile is 15 meters per second. And it's at a given angle, theta, of 20 degrees. Okay, you kick a ball literally with that velocity at that angle. Right off the bat, you should recognize that this ball is going to move in what directions? 2 directions it's going to move. Which 2 directions will this ball move? North and east. North and east, or up and right. Which is in the y direction, and it's also in the x direction. So I could think of this velocity as being broken into 2 parts. I could say, you know what? It's kind of like I'm kicking it to the right, like that, with the green arrow. And it's also like I'm kicking it up at the same time, with the blue arrow. And this is exactly what we've been doing all along. We've constantly been breaking things into their components of vectors. And we're going to do that again. So the blue arrow is just 15, sine of the angle. The green arrow is 15, cosine of the angle. And whatever those numbers turn out to be, 15 sine 20, 15 cos 20 in your calculator, right, are the velocities in each direction. One is in the x direction, and one is in the y direction. These are the initial velocities in the x and the y direction. Why do I do this? The reason I do this in these problems is simply because, you know what? I break up my problem into 2 directions. So I need to know their individual components. Because I'm looking at the x direction only, and then I look at the y direction only, and I kind of look at them separately, except for time, right? Time is our linking variable. Everything else needs to be specific to that direction. So in green here, this is VIX in green, also known as V bar x. And in blue, this is VIY. I'm calling this V bar x again. Why don't I have to call it initial or final in the x direction? I talked about this the other day. Who remembers? I talked about it the other day, why I don't need initial or final in the x direction ever.
Constant.
Because the velocity in the x is always constant. It's always constant. There's never any, what's the word? In the x, there's never any acceleration. That's right. But in the y direction, gravity accelerates all things. So although 15 sine 20 is what I'm starting with for velocity in the y direction, it will change. It will change. Okay, it will change dramatically. And I'm going to show you that actually before we get into the next problem. I'm going to show you a quick demo of that and how that looks. Yes?
So is that in the equation up there, VIX equals V times cosine theta?
Is really V bar x.
Oh, okay, so it's
exactly.
Okay.
Okay, so I call it VI, but because in this course we don't have acceleration in the x, we can say that this up here is really just v bar x. Okay, very good, Isabel. And that's important to note. She's just saying here, yeah, it says vi there. But that, again, in any like traditional physics course, you could have acceleration in the x. We're not going to, so you can simplify things by calling it v bar x because it's constant. Okay, it's constant the whole way. Good. Thanks. I appreciate it. Thanks so much.
See you later.
See you later, guys. I do want to chat with you later about something not with you, but something I need help on. So
Okay.
if you have time after school for like a minute, or if not, maybe tomorrow at some point, come by.
All right, I'll
We'll
probably.
figure it out. If not in class, I'll see you tomorrow for engineering.
Okay.
Okay? Thanks, guys.
No problem.
So when I look at these problems, I just got to consider them separately. All right? So I'm going to take a quick side note out of here. So pause the notes for a second and just watch what I'm going to show you here for a little bit. So you're going to use this